Good evening, everyone. Myself Gautam Sharma. I welcome you all in a Sapience Education. For more details, you can visit our website www.sapienceeducation.com. Okay, so let us go and discuss about the physics. That is, we are discussing moving charges and magnetism part 8 video. So basically, in this chapter, we will discuss about the moving coil galvanometer. Okay, now see here. A moving coil galvanometer. What is this? Moving coil galvanometer is an instrument used to for the detection and measurement of a small electric current and a voltage. If you want to find how much amount of electric current is there, what is the voltage, so you want this galvanometer. So what is the basic principle of the galvanometer? So let us understand. Its working is based on the fact that the when a current carrying, it is a current, okay, when a current carrying coil is placed in the magnetic field, it experiences a torque. So I have already done a video about this, how torque is being created. Now let us check the diagram. So this this is the axis of a rotation, okay. So this may be any metal, non-metal, whatever. And around this, a coil is being placed. See here, number of turns are there. Got it? And there is a spring on this. There is a spring. See here, there is a spring attached to it. Got it? There is a north as well as south magnetic field. Now you can see here. Now you can see that the magnetic field with the coil will be always radial. See here, magnetic field will be radial, radial like this. Magnetic field is radial like this, radial like this. So magnetic field is not a straight line, so it is like a radius. So from here we can observe, let us see here, this is your north pole, this is a north pole and this is a south pole, okay, and this is north pole, so this is the magnetic field radius, this is the radius, radial direction. So from north to south pole it is moving like this, okay, so it is like this. I hope you have understood. Now there is a spring, so this is the spring, you should try to understand. There is a spring, okay, this is a spring, so try to understand the structure, right? There is a spring attached to it which will restore the torque. Now let us suppose if you place any current carrying conductor in a constant magnetic field, so what will happen? A torque is being produced, okay, a torque is being produced. Now what will happen due to this torque? What will happen? A rotation will establish. Got it? Now, since it is a uniform radial magnetic field, so rotation will be established. So what will happen if a current will goes? So what will happen? A spring will restore it. Means a spring will try to move it in a original position. So it will give a restoring torque, right? Restoring torque. A spring will give you a restoring torque. Understood? Now, let us go for a construction as well. So I hope you have understood this. So let us go for a construction. The galvanometer is consist of a coil with many turns, which is the free to rotate about a fixed axis in a uniform radial magnetic field. And there is a cylindrical soft iron core which increase the strength of the magnetic field and makes the field radial. So this see here, we in place of any other thing, we are placing an iron core, soft iron core, soft iron core. So what actually happens? Soft iron core, what actually has, when it increase the magnetic field strength, it increases the magnetic field strength. Magnetic field strength. Okay. So what happen actually? There is a cylindrical soft iron core which is increase the strength of the magnetic field and makes the field radial. So why it is radial? See here. See, it is just like a circular arc like there. So radial means along the radius. Along the radius. See, magnetic field is along the radius. It is not like that. If let us suppose this is the coil like this, and it is not like that the magnetic field is moving like this. So it has been designed in such a way that that it is coming radial. See here, radial like this, like this. All magnetic field is coming towards center, and it is going from the center outward like this. Okay. So it has been designed that all are coming at the center, and again it's like this. See here, it's like this, 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 like this. Okay. Now let us go for the working. When a current flows through a coil, when a current flows through the coil, let us suppose when a current flows through a coil, a torque act on it, which can be given as torque is equal to NI to AB, what we have studied earlier. Now, you are thinking that, sir, why we are not putting NIAB sine theta? Definitely we are putting, but sine theta is equal to 1. Now you will tell me why, sir. So let us see here. Let us see the structure. See the structure here. The magnetic field, see here. Theta, the angle between magnetic field and the coil is always 90 degree. Right? See, this is your coil. This is the coil right now. Okay? This is the coil, and coil is a circular area, right? So the angle between magnetic field, see here, this is the magnetic field line, and it is a 90 degree. It is making an angle 90 degree with the magnetic field every time. So if you make a coil like this, let us suppose, see here, if you make a coil like this, see, if you're making a coil like this, so what will happen? Again, you will see that this magnetic field is making an angle 90 degree. So somehow you will find a magnetic field always make by design it has been made in a such a way that the theta is equal to 90 degrees. So sine 90 is equal to 1. Got it? So the magnetic torque tends to rotate the coil. So what will happen? A torque, see here, what will happen? A torque is being created. So let us suppose a torque is being created. So what will happen? A torque is being created like this and like this. So what will happen? It will try to rotate like this, or it may rotate like this depending upon the right hand Fleming's right hand rule. So the spring SP provides a counter torque K theta K phi that balances the magnetic torque NIAP and results in steady angular deflection phi. So you know that we have a spring attached to it. So let us see here. It is your spring attached to it. Okay, it will counter. Suppose it will move in this direction. So what will happen? Sorry, it will move in this direction. So spring will try to move in opposite direction. So spring will counter. So we know that spring force is equal to Kx. We have already studied in a class 11. That is minus Kx. But here it won't work. Why? Because it is a rotational torque. So torque is being there. So torque will be equal to K into theta. Not theta, it will be, let us suppose we are taking an angle phi. So this is known as restoring torque. This is known as restoring torque. Restoring torque, right? This is your restoring torque, and the torque being produced by this is equal to torque is which is being produced in the coil is equal to NIAB. So this torque will be restored by this torque. So we can directly say that both are equal. Okay. So if in equilibrium, suppose the coil is in equilibrium, so K phi will be equal to NIAB, where K is the torsional constant. Torsional constant. It is like a spring constant. You have studied in class 11 that spring constant K, spring constant K, spring constant K is there. So here in a torque, what will happen? A spring, a circular spring has a torsional constant. of the spring, that is restoring torque per unit twist, and K is known as restoring torque per unit twist. Now the deflection phi is indicated on the scale by a pointer attached to the spring coil. Now see here the structure. The structure is there. See here, if it is making an angle theta, if it is making an angle theta, let us suppose it is making an angle theta degree. So what will happen? It will move in this direction. Suppose it may move theta 5, sorry, phi 1. It may move like this, phi 2. The more it, the more it in this will move, it means that more current will flow. Why more current will flow? Let us understand. See here. Why more current will be flow? See here. Now we have phi is equal to NIABK. So number of turns are fixed. A is fixed, B is fixed, spring constant is fixed. But what is vary? Current is different. So if current will be different, so if current will increase, it means phi will increase. If current will decrease, it means phi will decrease. So from here we can measure the amount of angle increase, means we can say that amount of current is more. So in this way we can compare it, right? We can compare it. Hence deflection produced is proportional to the current flowing through the galvanometer. So the more deflection will be there, so more current will be flowed, right? So okay, so I hope you have understood this, the basis of the galvanometer. Now the thing is that what is current sensitivity? So current sensitivity, let us understand. It is defined as the deflection produced in a galvanometer per unit current. So that is phi by I. And if you put the value of phi, so finally we have got NBA by K. So if you want to find a current sensitivity, so you put the value of number of turns, magnetic field, area of the coil, and torsional spring constant. And the current sensitivity is radian per ampere, a division per ampere. So this is the current sensitivity. So if amount of deflection per unit current is very large, it means it is very sensitive. If the amount of deflection is low, so it has low current sensitivity. So how much it can sense, how much quickly it can respond, that is the current sensitivity, right? So I hope you have understood this current sensitivity. Now what is voltage sensitivity? It is defined as the deflection produced in a galvanometer when a unit voltage is applied across the two terminal galvanometer. So voltage sensitivity is equal to amount of deflection per unit voltage. Voltage V is equal to I into R. So put their value. So when we put their value, so we will get NBA by K into R. So the extra R will be imposed. So unit of voltage sensitivity is radius per volt or division per volt. So I hope it is an easy to understand this thing. Okay, it is an easy to understand this thing, right? So I hope you have understood this. Got it? Now what is ammeter? It is a, see, ammeter is the current measuring device, right? Ammeter is a low resistance galvanometer. It is used to measure the current in the circuit. So let us suppose the current is passing through it and I want to find the current. So I will connect the ammeter only. Now what is galvanometer? Galvanometer is very sensitive device. It gives a full scale deflection of the current in the order of microampere. So what happen if you will put a I ampere current, 1 ampere, 2 ampere, 10 ampere? So what will happen? It won't work because it is very sensitivity and it has only low range. So for measuring a current, galvanometer has to be connected in a series and it has a large resistance. So it will change the value of the current in the circuit, right? So to overcome, see here. So if you put a large resistance, so see ammeter, if you put a large resistance, so what will happen? It will change the value. So to cope up this type of thing, so what we need to do to overcome these difficulties, a low resistance wire RS called shunt resistance is connected in a parallel with the galvanometer coil so that most of the current will pass through the shunt. So what actually we are doing, sir, let us see. A current is going like this, and we have connected the galvanometer with the resistance Rg. Now I will connect a resistance with the low resistance. Low resistance, okay? So if there is a low resistance, so what will happen? Most of the 90% current will pass through this. So what will happen? There will be no impact on this galvanometer. No reduction in the current will happen. Earlier, what happens when we are using in the series directly? So what happens? What happens? Current have to. There is a reduction of a current due to the large resistance. So what we have done? We have done given a special path so that the current can pass through, and this is known as ammeter. So the effective resistance connected through is galvanometer into the ammeter is equal to Rg into Rs by Rg plus Rs. Why? Because both are in a parallel. So let us check it. See, Rg and Rs in parallel. So the effective resistance, net resistance will be Rg into resistance of galvanometer into resistance of a shunt divided by resistance of galvanometer plus resistance of the shunt. So to convert a galvanometer to ammeter, we use shunt in parallel. We use shunt in a parallel, right? And shunt is of low resistance. It is of low resistance. Shunt means extra resistance we are adding, right? So I hope you have understood this. Also, we know that Ig into Rg is equal to I minus Rg, I minus Ig into Rs. Why? Because voltage will be same. So at this point, voltage will be remain same because both are in parallel. So Ig into Rg will be equal to I minus Ig into Rs. So this is what we have done. So from here, R resistance of the shunt. If you want to find the resistance of the shunt, so you can use this formula like this. So an ideal ammeter has a zero resistance. So we will try to reduce this resistance to be zero. So this is an ideal resistance, ideal ammeter. If zero resistance will happen, so 99% current will try to move in the, if see here, if the resistance, shunt resistance is approximately zero, so most of the current will go through it. And our main motto is to measure the current, right? So without using much current, so most of the current will pass through it. So what will happen? We will able to measure the amount of current, how much ampere it is, right? So I hope you have understood this. Now, now it is a turn of voltmeter. A voltmeter is a high resistance galvanometer. So ammeter, what happened? Low resistance, it was a low resistance, but in a voltmeter, it is a high resistance galvanometer. It is used to measure the potential difference between the 2 points of the circuit in a volt. A galvanometer can be converted into voltmeter by connecting a high resistance in a series with the galvanometer so that it will draw a small current. Otherwise, voltage measurement will disturb the original setup by an amount which is large. So first of all, you need to understand that if you want to if you want to measure the voltage, so you have to connect the voltmeter into the parallel. So let us suppose this is a galvanometer having a resistance Ig. Now what I will do, I will connect this into the series. See here, I will connect this into the series. So what will happen? What will happen? This is suppose shunt resistance or extra resistance we have done. So what will happen? This is the voltmeter. This whole combined become voltmeter. So when you connect galvanometer having a resistance Rg with the extra shunt resistance R, so this will become a voltmeter. And now this will be connected in the parallel circuit. So if you want to find a voltage across this, so you have to connect it parallel. So what will happen if suppose 100 ampere current is there? So it will mainly pass through this. But what we have done, we have given heavy amount of resistance. So there will be less amount of current which will pass. So what will happen? No wastage of current will happen. So most of the 99% will pass through the circuit. Got it? So our main motto was that most of the current should pass directly without coming into the galvanometer. In this to measure the voltage. Now tell me if, now tell me, now tell me, this is the galvanometer resistance and this is your shunt resistance. This is your shunt resistance, right? So if you add this, so total resistance will be Rg plus R. Okay, so the effective resistance of the converted galvanometer into voltmeter, that is Rs, is equal to Rg plus R. So this, sorry, Rg plus R. So from Ohm's law, what will happen? R is equal to V by I. See here, R will be Rs minus Rg. So Rs is the voltage by current in the galvanometer, right? From Ohm's law, Ig is equal to V by, see, from current in the galvanometer is equal to voltage by Rg, Rg plus R, total resistance. So this is Ig. So from here, Rg plus R is equal to, see here, let us do it properly. See, what actually happens, Ig, that is current in the galvanometer, will be equal to voltage divided by total resistance, that is Rg plus R. So this is your Rg plus R. Okay, is it okay? Now we have understood that total resistance, effective resistance, is equal to, that is Rs is equal to Rg plus R. Now from here, the resistance, that is shunt resistance. See, this is total resistance in a series, right? Resistance in the series. Okay. Now tell me, R, that is shunt resistance, R will be equal to Rs minus Rg. So this is the resistance of the galvanometer. What is the resistance of the total series? Resistance is equal to, tell me, this is total resistance. So V by Ig. So we can write this is a Rs. Rs is equal to Rg plus Rm. So from here we can write V by Ig, and this is equal to Rg plus R. So Rg plus R is your Rs, resistance in a series. So we can put here V by Ig and minus Rg. So what we have got? So the resistance of an ideal voltmeter is infinity. So we will try to create an increase very high amount of resistance so that minimum amount of current will flow and we can measure the voltage without losing the voltage drop. So this is the way to find it. I hope you have understood this. Okay. So thanks for watching my video. I hope you have understood well. So if you have any doubt or anything, so you can directly contact us. Thank you for watching my video.